this lecture we are going to define the determinant that we introduced in the previous lecture. The best way to define determinant is to use the Laplace expression. So let A to be the matrix with coefficients aij, and A is going to be an n by n matrix. So we are going to define the determinant as we said in the previous lecture, just for square matrices. And we denote by AK1, AK2, and so on, kth row. Then we have the following equality. So the determinant of A can be expressed as this summation over the index j of these terms, -1 to the power k plus j times A, the coefficient akj, times the determinant of this matrix, which we will denote by akj, and akj has the following expression. So we can derive akj from the matrix A. So here I just wrote the coefficients of the matrix A. So in order to derive akj, we have to remove the jth column and the kth row. What it will remain, it is an n minus 1 by n minus 1 matrix with coefficients inherited by the matrix A. If we look carefully at this formula, we will notice that this expression depends on the row, the kth row that we have chosen. So k can be 1, 2, 3, or so on, or up to n. So it looks like that this formula might depend on the index k, so on the row we choose to expand the determinant along. But in fact it is a result that this expression will change if we change k, but the result of this summation will always be the same, and will always be equal to the same number, which we call determinant of A. So the formula depends on the row k, meaning the expression of the formula. The expression will depend on the row k, but the determinant does not. And there is a similar expansion of the determinant. Instead of expanding it through a row, so picking up the coefficients akj through a row, we can pick them up inside a column. So there is a similar expression of the determinant through an h column instead of the kth row. Explicitly, the formula reads as follows. So the determinant of A equals summation for I that goes 1 to n of -1 to the power I plus h times aih. So when we vary I in this formula, aih will run through the h column, as opposed to running through the kth row implied by the previous formula, where we were making vary the second index instead of the first of these coefficients. And then we multiply this coefficient by the determinant of aih, which is defined exactly as we just did for the previous formula. The next thing to notice is that these are recursive definitions. So if you see, the determinant of a n by n matrix called A is expressed in function of certain coefficients of A, and then a determinant of a n minus 1 by n minus 1 matrix. Therefore, we assume to have the definition for n minus 1 by n minus 1 by n minus 1 matrix, and using that definition we can define for the matrix of the next order. Let's pick an example example 1, given that determinant of A equals to A, so determinant of a matrix, 1 by 1 matrix, is the matrix itself, which in this case is just a scalar. Remember that the determinant is a function that goes from the set of matrices, n by n matrices, to the real numbers. So in this case, n equals to 1, so a matrix is just a scalar, and we can prove that a multilinear function which is alternating and for which the value on the identity matrix is 1, in this case is just the identity. So given that the determinant of A equals to A, we will write the formula for the determinant of a generic 2 by 2 matrix and check it coincides with the one we derived in lecture 7.1. Remember that in that lecture we showed that applying the defining rules of the determinant, we can show that there will be a unique function respecting these rules, and this unique function had an explicit expression in function of the coefficients of the matrices. So let's see if we can recover the same expression using the Laplace formula instead. Let denote A by the matrix with coefficients A, B, C, D. Exactly the same notation we used in previous lecture, in lecture 7.1. We will use the expansion of Laplace formula along the first row. So the determinant of this matrix is going to be equal to, let's see, I reported here on the bottom the general formula for row expansion of the determinant using the Laplace formula. So we will apply this in this particular case. So we have the expansion along the first row. The first summand will be relative to the coefficient A, and the second summand will be relative to the coefficient B of the first row. The determinant is going to be expressed then with the formula -1 raised to the power k plus j. And in this case, k is 1 because it's the first row. J is the coefficient of the first row we are considering in this summand. The first coefficient of the first row will have k equals to 1 because it's the first row, and j equals to 1 because it's the first coefficient. So 1 plus 1 times a, okay, a is the coefficient relative to the first summand, times the determinant of the matrix we obtain deleting the first row and the first column. These are the the row and column associated to the coefficient we are considering, which is A. So what remains from this matrix is just a submatrix reduced to the coefficient D. And we just say, okay, determinant of D, this is the submatrix. Second summand is the one relative to the scalar B, which is the second scalar of the first row. K is going to be 1 and J is going to be 2 because it's the second scalar. The power to which we have to raise -1 is going to be 1 plus 2, and the coefficient in which we are considering is B, so times B, times the determinant of the submatrix, which we get by deleting the first row and the second column, which are the row and the column associated to the scalar B that we are considering. So this submatrix is reduced just to the coefficient C, so times the determinant of C. Now we know the determinant of D and the determinant of C, which are just D and C respectively. This formula reduces to A because it's -1 raised to the power 2, which is plus 1, so A times D, which is the determinant of D, minus B times determinant of C, which is C, so in this case it's going to be -1 raised to the power 3. Therefore the formula we get is A times D minus B times C, which is exactly the same formula we derived in lecture 7.1. The second example we are going to consider is the following. It is the determinant of a 3 by 3 matrix, a numerical one in this case. We can derive also the generic formula for a 3 by 3 matrix, but I suggest to just remember the Laplace formula and apply it every time we have a matrix, rather than trying to remember the explicit generic expression of the determinant of an n by n matrix in a polynomial form. This has the advantage that we just have to remember one formula instead of a certain number of them, except for n equals to 2. The formula is very, very easy, so in that case we can just remember and not derive it every time using the Laplace expansion. So we again expand the determinant along one row. Notice that it is always convenient to choose a row with the highest number of zeros in it, because the Laplace expansion that we have here on the bottom, we see that we have, for an n by n matrix, the determinant is expressed as a n tuple sum, so we have n summands. Each of the summands is of the form, well, a certain numerical coefficient, which might be made -1 or 1, times akj. Now these are scalars that vary along one row if we expand the determinant along one row. If this row has a lot of zeros, automatically we will have several of these summands that will be zeros. We don't even have to compute this determinant of these submatrices, because if the coefficient in front will be 0, then we just skip that summand. That implies that in this particular case we have a possible choice of the first, expanding along the first row or the second row, because in both of these cases we have 1 0, whereas in the third row we have no 0. So the expansion of the third row will involve the 3 summands that we have to compute, whereas expanding it along the first row or the second row, we'll just have 2 summands, because there is 1 0, and that summand corresponding to the zeros will be 0. Now either we choose the first or the second row. Say we pick the second row. The determinant of this matrix is going to be equal to, let's expand along the second row as we said. So we have 3 coefficients, we actually reduce to 2, just 1 and then 1 again, because the last one is going to be 0, so that summand is automatically 0. The first summand is relative to 1, the first coefficient 1. We have -1 raised to the power. We have to, the power is going to be a sum of the 2 indices of the coefficient 1. So this coefficient 1 corresponds to the second row and the first column. The power to which we raise -1 is going to be 2 as the second row plus 1 as the first column, times the coefficient itself, which is 1, times the determinant of the submatrix we obtain, removing the first column and the second row. Okay, so this is precisely the 2 by 2 matrix, submatrix we obtain from A, deleting the first column and the second row. Then the second summand is going to be relative to the coefficient 1, corresponding to the second row and the second column. So -1 will be raised to the power 2 plus 2, multiplied by 1, the coefficient, multiplied by the determinant of a submatrix we obtain removing the second row and the second column. And the matrix remaining will have as the first row the number 2 here and 1, and then as a second row -1 and 2. We have an expression of the determinant as 2 summands, of which we have to compute one determinant each of a 2 by 2 matrix, of which we know the formula that we already computed in 2 different ways. Finally we get this number, so -1 to the power 2 plus 1 is -1 to the power 3, so we'll have a negative here. and then times 1, which leaves unchanged the determinant. Determinant of this matrix is going to be A times D, so 0 times 2, minus B times C, negative 3. We have a minus here coming from this coefficient, and then negative 3 coming from the determinant, plus negative 1 to the power of 4, which is plus 1. We have a plus here. 1 times determinant of this matrix is equal to A times D, so 2 times 2, which is 4, minus B times C. B is 1, C is negative 1. So we have minus negative 1, which is plus 1. And the result is 8.